The Disappearing Spoon, and Other True Tales of Madness, Love, and the History of the World from the Periodic Table of the Elements. By Sam Kean. Narrated by Runnette. Copyright 2010 by Sam Kean. This unabridged audiobook is published by arrangement with Little Brown and Company, a division of Hachette Book Group, Incorporated, and was produced in the year 2010 by Tantor Media, Incorporated, which holds the copyright thereto. Publisher's note: should you wish to refer to the periodic table at any time, please visit our website at www.tantor.com, keyword disappearing spoon. Introduction. Mercury. As a child in the early 1980s, I tended to talk with things in my mouth. Food, dentist tubes, balloons that would fly away, whatever. And if no one else was around, I'd talk anyway. This habit led to my fascination with the periodic table the first time I was left alone with a thermometer under my tongue. I came down with strep throat something like a dozen times in the second and third grades, and for days on end it would hurt to swallow. I didn't mind staying home from school and medicating myself with vanilla ice cream and chocolate sauce. Being sick always gave me another chance to break an old-fashioned mercury thermometer, too. Lying there with the glass stick under my tongue, I would answer an imagined question out loud, and the thermometer would slip from my mouth and shatter on the hardwood floor, the liquid mercury in the bulb scattering like ball bearings. A minute later, my mother would drop to the floor, despite her arthritic hip, and begin corralling the balls. Using a toothpick like a hockey stick, she'd brush the supple spheres toward one another until they almost touched. Suddenly, with a final nudge, one sphere would gulp the other. A single seamless ball would be left quivering where there had been two. She'd repeat this magic trick over and over across the floor, one large ball swallowing the others until the entire silver lentil was reconstructed. Once she'd gathered every bit of mercury, she'd take down the green-labeled plastic pill bottle that we kept on a knick-knack shelf in the kitchen between a teddy bear with a fishing pole and a blue ceramic mug from a 1985 family reunion. After rolling the ball into an envelope, she'd carefully pour the latest thermometer's worth of mercury onto the pecan-sized glob in the bottle. Sometimes, before hiding the bottle away, she'd pour the quicksilver into the lid and let my siblings and me watch the futuristic metal whisk around, always splitting and healing itself flawlessly. I felt pangs for children whose mothers so feared mercury they wouldn't even let them eat tuna. Medieval alchemists, despite their lust for gold, considered mercury the most potent and poetic substance in the universe. As a child, I would have agreed with them. I would have even believed, as they did, that it transcended pedestrian categories of liquid or solid, metal or water, heaven or hell, that it housed otherworldly spirits. Mercury acts this way, I later found out, because it is an element. Unlike water, H2O, or carbon dioxide, CO2, or almost anything else you encounter day to day, you cannot naturally separate mercury into smaller units. In fact, mercury is one of the more cultish elements. Its atoms want to keep company only with other mercury atoms, and they minimize contact with the outside world by crouching into a sphere. Most liquids I spilled as a child weren't like that. Water tumbled all over, as did oil, vinegar, and unset jello. Mercury never left a speck. My parents always warned me to wear shoes whenever I dropped a thermometer, to prevent those invisible glass shards from getting into my feet, but I never recall warnings about stray mercury. For a long time I kept an eye out for element 80, at school and in books, as you might watch for a childhood friend's name in the newspaper. I'm from the Great Plains and had learned in history class that Lewis and Clark had trekked through South Dakota and the rest of the Louisiana Territory with a microscope, compasses, sextant, 3 mercury thermometers, and other instruments. What I didn't know at first is that they also carried with them 600 mercury laxatives, each 4 times the size of an aspirin. The laxatives were called Dr. Rush's bilious pills, after Benjamin Rush, a signer of the Declaration of Independence and a medical hero for bravely staying in Philadelphia during a yellow fever epidemic in 1793. His pet treatment for any disease was a mercury chloride sludge administered orally. Despite the progress medicine made overall between 1400 and 1800, doctors in that era remained closer to medicine men than medical men. With a sort of sympathetic magic, they figured that beautiful, alluring mercury could cure patients by bringing them to an ugly crisis, poison fighting poison. Dr. Rush made patients ingest the solution until they drooled, and often people's teeth and hair fell out after weeks or months of continuous treatment. His cure no doubt poisoned or outright killed swaths of people whom yellow fever might have spared. Even so, having perfected his treatment in Philadelphia, 10 years later he sent Meriwether and William off with some prepackaged samples. As a handy side effect, Dr. Rush's pills have enabled modern archaeologists to track down campsites used by the explorers. With the weird food and questionable water they encountered in the wild, someone in their party was always queasy, and to this day mercury deposits dot the soil many places where the gang dug a latrine, perhaps after one of Dr. Rush's thunderclappers had worked a little too well. Mercury also came up in science class. When first presented with the jumble of the periodic table, I scanned for mercury and couldn't find it. It is there, between gold, which is also dense and soft, and thallium, which is also poisonous. But the symbol for mercury, Hg, consists of 2 letters that don't even appear in its name. Unraveling that mystery, it's from hydrogerum, Latin for water silver, helped me understand how heavily ancient languages and mythology influenced the periodic table, something you can still see in the Latin names for the newer, super-heavy elements along the bottom row. I found mercury in literature class as well. Hat manufacturers once used a bright orange mercury wash to separate fur from pelts, and the common hatters who dredged around in the steamy vats, like the mad one in Alice in Wonderland, gradually lost their hair and wits. Eventually, I realized how poisonous mercury is. That explained why Dr. Rush's bilious pills purged the bowels so well. The body will rid itself of any poison, mercury included. And as toxic as swallowing mercury is, its fumes are worse. They fray the wires in the central nervous system and burn holes in the brain, much as advanced Alzheimer's disease does. But the more I learned about the dangers of mercury, the more, like William Blake's Tiger, Tiger, Burning Bright, its destructive beauty attracted me. Over the years, my parents redecorated their kitchen and took down the shelf with the mug and teddy bear, but they kept the knickknacks together in a cardboard box. On a recent visit, I dug out the green-labeled bottle and opened it. Tilting it back and forth, I could feel the weight inside, sliding in a circle. When I peeked over the rim, my eyes fixed on the tiny bits that had splashed to the sides of the main channel. They just sat there, glistening, like beads of water so perfect you'd encounter them only in fantasies. All throughout my childhood, I associated spilled mercury with a fever. This time, knowing the fearful symmetry of those little spheres, I felt a chill. From that one element I learned history, etymology, alchemy, mythology, literature, poison forensics, and psychology. And those weren't the only elemental stories I collected, especially after I immersed myself in scientific studies in college and found a few professors who gladly set aside their research for a little science chit-chat. As a physics major with hopes of escaping the lab to write, I felt miserable among the serious and gifted young scientists in my classes who loved trial-and-error experiments in a way I never could. I stuck out 5 frigid years in Minnesota and ended up with an honors degree in physics, but despite spending hundreds of hours in labs, despite memorizing thousands of equations, despite drawing tens of thousands of diagrams with frictionless pulleys and ramps, my real education was in my professors' stories. Stories about Gandhi and Godzilla and a eugenicist who used geranium to steal a Nobel Prize. About throwing blocks of explosive sodium into rivers and killing fish. About people suffocating, quite blissfully, on nitrogen gas in space shuttles. About a former professor on my campus who would experiment on the plutonium-powered pacemaker inside his own chest, speeding it up and slowing it down by standing next to and fiddling with giant magnetic coils. I latched onto those tales, and recently, while reminiscing about Mercury over breakfast, I realized that there's a funny or odd or chilling tale attached to every element on the periodic table. At the same time, the table is one of the great intellectual achievements of humankind. It's both a scientific accomplishment and a storybook, and I wrote this book to peel back all of its layers one by one, like the transparencies in an anatomy textbook that tell the same story at different depths. At its simplest level, the periodic table catalogues all the different kinds of matter in our universe, the 100-odd characters whose headstrong personalities give rise to everything we see and touch. The shape of the table also gives us scientific clues as to how those personalities mingle with one another in crowds. On a slightly more complicated level, the periodic table encodes all sorts of forensic information about where every kind of atom came from and which atoms can fragment or mutate into different atoms. These atoms also naturally combine into dynamic systems like living creatures, and the periodic table predicts how. It even predicts what corridors of nefarious elements can hobble or destroy living things. The periodic table is, finally, an anthropological marvel, a human artifact that reflects all of the wonderful and artful and ugly aspects of human beings and how we interact with the physical world, the history of our species written in a compact and elegant script. It deserves study on each of these levels, starting with the most elementary and moving gradually upward in complexity. And beyond just entertaining us, the tales of the periodic table provide a way of understanding it that never appears in textbooks or lab manuals. We eat and breathe the periodic table. People bet and lose huge sums on it. Philosophers use it to probe the meaning of science. It poisons people. It spawns wars. Between hydrogen at the top left and man-made impossibilities lurking along the bottom, you can find bubbles, bombs, money, alchemy, petty politics, history, poison, crime, and love, and even some science. Part 1. Orientation, column by column, row by row. Chapter 1. Geography is destiny. Helium, boron, antimony, thulium, oxygen, holmium. When most people think of the periodic table, they remember a chart hanging on the front wall of their high school chemistry class, an asymmetric expanse of columns and rows looming over one of the teacher's shoulders. The chart was usually enormous, 6 by 4 feet or so, a size both daunting and appropriate given its importance to chemistry. It was introduced to the class in early September and was still relevant in late May, and it was the one piece of scientific information that, unlike lecture notes or textbooks, you were encouraged to consult during exams. Of course, part of the frustration you might remember about the periodic table could flow from the fact that, despite its being freely available to fall back on, a gigantic and fully sanctioned cheat sheet, it remained less than frickin' helpful. On the one hand, the periodic table seemed organized and honed, almost German-engineered for maximum scientific utility. On the other hand, it was such a jumble of long numbers, abbreviations, and what looked for all the world like computer error messages, XE6S2 4FL1 5D1, it was hard not to feel anxious. And although the periodic table obviously had something to do with other sciences, such as biology and physics, it wasn't clear what exactly. Probably the biggest frustration for many students was that the people who got the periodic table, who could really unpack how it worked, could pull so many facts from it with such dweeby nonchalance. It was the same irritation colorblind people must feel when the fully sighted find 7s and 9s lurking inside those party-colored dot diagrams. Crucial but hidden information that never quite resolves itself into coherence. People remember the table with a mix of fascination, fondness, inadequacy, and loathing. Before introducing the periodic table, every teacher should strip away all the clutter and have students just stare at the thing. Blank. What does it look like? Sort of like a castle, with an uneven main wall as if the royal masons hadn't quite finished building up the left-hand side, and tall defensive turrets on both ends. It has 18 jagged columns and 7 horizontal rows, each with a landing strip of 2 extra rows hanging below. The castle is made of bricks, and the first non-obvious thing about it is that the bricks are not interchangeable. Each brick is an element, or type of substance. As of now, 112 elements, with a few more pending, make up the table, and the entire castle would crumble if any of those bricks didn't sit exactly where it does. That's no exaggeration. If scientists determined that one element somehow fit into a different slot, or that 2 of the elements could be swapped, the entire edifice would tumble down. Another architectural curiosity is that the castle is made up of different materials in different areas. That is, not all the bricks are made of the same substance, nor do they have the same characteristics. 75% of the bricks are metals, which means most elements are cold, gray solids, at least at temperatures human beings are used to. A few columns on the eastern side contain gases. Only 2 elements, mercury and bromine, are liquids at room temperature. In between the metals and gases, about where Kentucky sits on a U.S. map, lie some hard-to-define elements whose amorphous nature gives them interesting properties, such as the ability to make acids billions of times stronger than anything locked up in the chemical supply room. Overall, if each brick was made of the substance it represented, the castle of the elements would be a chimera, with additions and wings from incongruent eras, or, more charitably, a Daniel Libeskind building with seemingly incompatible materials grafted together into an elegant whole. The reason for lingering over the blueprints of the castle walls is that the coordinates of an element determine nearly everything scientifically interesting about it. For each element, its geography is its destiny. In fact, now that you have a sense of what the table looks like in outline, I can switch to a more useful metaphor: the periodic table as a map. And to sketch in a bit more detail, I'm going to plot this map from east to west, lingering over both well-known and out-of-the-way elements. First up, in column 18 at the far right-hand side, is a set of elements known as the noble gases. Noble is an archaic, funny-sounding word, less chemistry than ethics or philosophy. And indeed, the term noble gases goes back to the birthplace of Western philosophy, ancient Greece. There, after his fellow Greeks Leucippus and Democritus invented the idea of atoms, Plato minted the word elements, in Greek stoicheia, as a general term for different small particles of matter. Plato, who left Athens for his own safety after the death of his mentor Socrates around 400 BC and wandered around writing philosophy for years, of course lacked knowledge of what an element really is in chemistry terms. But if he had known, he no doubt would have selected the elements on the eastern edge of the table, especially helium, as his favorites. In his dialogue on love and the erotic, the Symposium, Plato claimed that every being longs to find its complement, its missing half. When applied to people, this implies passion and sex and all the troubles that accompany passion and sex. In addition, Plato emphasized throughout his dialogues that abstract and unchanging things are intrinsically more noble than things that grub around and interact with gross matter. This explains why he adored geometry, with its idealized circles and cubes, objects perceptible only to our reason. For non-mathematical objects, Plato developed a theory of forms which argued that all objects are shadows of one ideal type. All trees, for instance, are imperfect copies of an ideal tree, whose perfect tree-ness they aspire to. The same with fish and fishness, or even cups and cupness. Plato believed that these forms were not merely theoretical, but actually existed, even if they floated around in an empyrean realm beyond the direct perception of humans. He would have been as shocked as anyone then when scientists began conjuring up ideal forms on Earth with helium. In 1911, a Dutch-German scientist was cooling mercury with liquid helium when he discovered that below negative 452 degrees Fahrenheit, the system lost all electrical resistance and became an ideal conductor. This would be sort of like cooling an iPod down to hundreds of degrees below zero and finding that the battery remained fully charged no matter how long or loud you played music, until infinity, as long as the helium kept the circuitry cold. A Russian-Canadian team pulled an even neater trick in 1937 with pure helium. When cooled down to negative 456 degrees Fahrenheit, helium turned into a superfluid with exactly zero viscosity and zero resistance to flow. Perfect fluidness. Superfluid helium defies gravity and flows uphill and over walls. At the time, these were flabbergasting finds. Scientists often fudge and pretend that effects like friction equal zero, but only to simplify calculations. Not even Plato predicted that someone would actually find one of his ideal forms. Helium is also the best example of elementness, a substance that cannot be broken down or altered by normal chemical means. It took scientists 2,200 years, from Greece in 400 BC to Europe in 1800 AD, to grasp what elements really are, because most are too changeable. It was hard to see what made carbon carbon when it appeared in thousands of compounds, all with different properties. Today we would say that carbon dioxide, for instance, isn't an element because one molecule of it divides into carbon and oxygen. But carbon and oxygen are elements because you cannot divide them more finely without destroying them. Returning to the theme of the symposium and Plato's theory of erotic longing for a missing half, we find that virtually every element seeks out other atoms to form bonds with, bonds that mask its nature. Even most pure elements, such as oxygen molecules in the air, O2, always appear as composites in nature. Yet scientists might have figured out what elements are much sooner had they known about helium, which has never reacted with another substance, has never been anything but a pure element. Author's note: two scientists observed the first evidence for helium, an unknown spectral line in the yellow range, during an eclipse in 1868, hence the element's name, from Helios, Greek for sun. The element was not isolated on Earth until 1895, through the careful isolation of helium from rocks. For more on this, see Chapter 17. For 8 years, helium was thought to exist on Earth in minute quantities only, until miners found a huge underground cache in Kansas in 1903. They had tried to light the gas shooting out of a vent in the ground on fire, but it wouldn't catch. Helium acts this way for a reason. All atoms contain negative particles called electrons, which reside in different tiers or energy levels inside the atom. The levels are nested concentrically inside each other, and each level needs a certain number of electrons to fill itself and feel satisfied. In the innermost level, that number is 2. In other levels, it's usually 8. Elements normally have equal numbers of negative electrons and positive particles called protons, so they're electrically neutral. Electrons, however, can be freely traded between atoms, and when atoms lose or gain electrons, they form charged atoms called ions. What's important to know is that atoms fill their inner lower energy levels as full as possible with their own electrons, then either shed, share, or steal electrons to secure the right number in the outermost level. Some elements share or trade electrons diplomatically, while others act very, very nasty. That's half of chemistry in one sentence. Atoms that don't have enough electrons in the outer level will fight, barter, beg, make and break alliances, or do whatever they must to get the right number. Helium, element 2, has exactly the number of electrons it needs to fill its only level. This closed configuration gives helium tremendous independence because it doesn't need to interact with other atoms or share or steal electrons to feel satisfied. Helium has found its erotic complement in itself. What's more, that same configuration extends down the entire 18th column beneath helium, the gases neon, argon, krypton, xenon, and radon. All these elements have closed shells with full complements of electrons, so none of them reacts with anything under normal conditions. That's why, despite all the fervid activity to identify and label elements in the 1800s, including the development of the periodic table itself, no one isolated a single gas from column 18 before 1895. That aloofness from everyday experience, so like his ideal spheres and triangles, would have charmed Plato. And it was that sense the scientists who discovered helium and its brethren on Earth were trying to evoke with the name noble gases. Or, to put it in Plato-like words, he who adores the perfect and unchangeable and scorns the corruptible and ignoble will prefer the noble gases by far to all other elements. For they never vary, never waver, never pander to other elements like hoi polloi offering cheap wares in the marketplace. They are incorruptible and ideal. The repose of the noble gases is rare, however. One column to the west sits the most energetic and reactive gases on the periodic table, the halogens. And if you think of the table wrapping around like a Mercator map so that east meets west and column 18 meets column 1, even more violent elements appear on the western edge, the alkali metals. The pacifist noble gases are a demilitarized zone surrounded by unstable neighbors. Despite being normal metals in some ways, the alkalis, instead of rusting or corroding, can spontaneously combust in air or water. They also form an alliance of interests with the halogen gases. The halogens have 7 electrons in the outer layer, one short of the octet they need, while the alkalis have 1 electron in the outer level and a full octet in the level below. So it's natural for the latter to dump their extra electron on the former and for the resulting positive and negative ions to form strong links. This sort of linking happens all the time, and for this reason electrons are the most important part of an atom. They take up virtually all an atom's space, like clouds swirling around an atom's compact core, the nucleus. That's true even though the components of the nucleus, protons and neutrons, are far bigger than individual electrons. If an atom were blown up to the size of a sports stadium, the proton-rich nucleus would be a tennis ball at the 50-yard line. Electrons would be pinheads flashing around it, but flying so fast and knocking into you so many times per second that you wouldn't be able to enter the stadium. They'd feel like a solid wall. As a result, whenever atoms touch, the buried nucleus is mute. Only the electrons matter. Author's note: to reiterate the point about atoms being mostly empty space, Alan Blackman, a chemist at the University of Otago in New Zealand, wrote in the January 28, 2008 Otago Daily Times, "Consider the most dense known element, iridium. A sample of this, the size of a tennis ball, would weigh just over 3 kilograms, 6.6 pounds. Let's assume that we could somehow pack the iridium nuclei together as tight as we possibly could, thereby eliminating most of that empty space. A tennis ball-sized sample of this compacted material would now weigh an astonishing 7 trillion tons, 7.7 trillion U.S. tons. As a footnote to this footnote, no one really knows whether iridium is the densest element. Its density is so close to osmium's that scientists cannot distinguish between them, and in the past few decades they've traded places as king of the mountain. Osmium is on top at the moment. One quick caveat: don't get too attached to the image of electrons as discrete pinheads flashing about a solid core, or in the more usual metaphor, don't necessarily think of electrons as planets circling a nucleic sun. The planet analogy is useful, but as with any analogy, it's easy to take too far, as some renowned scientists have found out to their chagrin. Bonding between ions explains why combinations of halogens and alkalis, such as sodium chloride, table salt, are common. Similarly, elements from columns with 2 extra electrons, such as calcium, and elements from columns that need 2 extra electrons, such as oxygen, frequently align themselves. It's the easiest way to meet everyone's needs. Elements from non-reciprocal columns also match up according to the same laws. Two ions of sodium, Na+, take on one of oxygen, O2, to form sodium oxide, Na2O. Calcium chloride combines as CaCl2 for the same reasons. Overall, you can usually tell it a...
Sample complete. Ready to continue?